Oh. All right, let's get started. So first thing, sign-in sheet. Now, let's deal with some housekeeping items. So number one, you all have your homework 9 due right now. Has everybody turned that in? I have. Homework 9. And the sign-in sheet's going around. So.
I know.
You had your chance to ask that question. We're going to move on from that one. I'll just... I didn't know about that. Okay, 1, 2, 3, 4, 5. He's saying Google's a wonderful thing. Okay, all right. So the homework 9 solution is being distributed as we speak. You all should have turned in your homework 9, so there's that. Your exam's on Monday, so I'm going to be honest with you, I can't make any promises about you getting homework returned back to you before the exam. All I can say is you have the solution, and I will do my best to get it graded as quick as humanly possible. So there's that. Let's talk about course evals. I mentioned something in Steel Design, and I'll do the same thing in here. So I sent some emails last night to a few of you that had yet to completed your course eval or had yet to tell me that you had completed your course eval. I'm giving 5 points, bonus homework points for anybody that does it, but if I get a 100% response, I'll grant 10 bonus points total to the class. So you'll have 10 instead of 5, but I got to have everybody, okay? The only thing I can see is how many people have completed it. So there's 27 people in the class, and the last time I checked, I think there was maybe 22 or 23, so there's still 4 or 5 of you that hadn't done your course evals. If you do it, and I get a 100%, I'll give everybody 10 points, but I got to have everybody, okay? What's that? Well, there's 100 possible points in the exam. All right, let's talk about homework 9 real quick. What's this? Oh, okay. I don't really think there's a whole lot to say about the solution. I mean, problem 1 was literally just VPN, just calculated, and it ended up being about 570 some kips. Problem 2, you had a design of a circular column. Go through and do the math. Now keep in mind this is a circle, not a square, so because of that, you could have 9 bars or what have you. It doesn't have to be even. I mean, you can, but it doesn't have to be because they're just going to evenly space it around the spiral. So the solution that I derived was really the one that was in the book, which was using 9 number 10s. So there's that. For problem 3, really the long and short of it is this. You should have gotten a KN of 0.579 and RN of 0.193. Go through and do the interpolation. You should get a row of 0.027, bless you. And you should ultimately use 6 number 9s. Here's the alignment chart, or the interaction diagrams, and I drew the lines, you know, how I'm getting those particular values. So that way you can kind of see that. Sound good? When it was all said and done, the row was 0.027. Bless you. So ultimately, I ended up needing 6 number 9s. So it was a pretty straightforward assignment. Sound good? Yep. All right, let's talk about the exam. The exam is going to be on columns, beam columns, and development length. That's going to be on this exam. Yes. Yes. All right. Let's talk about the scheduling. So and the housekeeping, closed book and closed notes. You've got a oh, yep. That's not a mistake. I could have just said, you know what? No. No, I'm good. Pass those out. Let me know if somebody's missing one. I feel like somebody might be missing one. Did you all already get yours in the back? Solution? All right. Does everybody have a solution and an exam 3 review? Okay. Let's talk about the exam. So, closed book and closed notes, you all know the drill. You'll be allowed a calculator and a formula sheet. Put whatever you want on that formula sheet except for workout examples. You all know the drill. We are starting the exam 10:15, Monday, May the 1st. So that is in 3 days. So 10:15, be in here ready to go. We'll have scratch paper. We'll have staplers. It's not a big deal. Also, any of the beam rebar sizes, the analysis aids, the interaction curves, you'll have any of those that you need. So that's not a big deal. It would probably not be the worst idea in the world to write down some fundamental beam analysis or any of those fundamental formulas, but you know, anything esoteric you'll be provided. That's not a big deal. Topics: development length. Make sure you can identify the parameters that may affect it. You know, bar coding, bar size, bar location. Be able to compute development length for straight bars and for hooks, and be able to perform any and all reductions that go along with that. Columns. Make sure you can analyze and design square and circular columns. You know, be able to assess all the detailing requirements as well. You know, spacing, all that stuff. Beam columns. Make sure that you can use your interaction diagrams. For provisions for development length, I did my best to try and take the lecture notes and squeeze it into as few slides as possible, but there's just a lot of provisions, so there's really not much I can do about that. So here's your fundamental development length equation. Remember, you can reduce that. That product is always taken to be less than or equal to 1.7. Here's your reinforcement location factor, your reinforcement size factor, your bar coding factor, your effects of spacing and cover. Let's see, your transverse reinforcement index, your development length for hooks, and as well as you can reduce that also. Cover factors and confinement factors, as well as the appropriate diagrams. Your phi-PN for axially loaded elements, knowing your different phis and alphas. Your reinforcement requirements for cast-in-place columns. Additional requirements for tied columns. Additional requirements for tied columns on your bar spacing. Spiral steel requirements for circular columns. Design of columns. I know I'm going through this kind of fast, but you all have it in front of you. And beam column design. I know that seems like a lot, but it's really just a lot of provision stuff. Stuff that you all could probably transfer onto a formula sheet with relative ease. Yeah. 7 was serviceability, right? Bless you. That's right, yeah, 8 and 9. Bless you. 8 and 9. So with that, it's your turn.
Could you go to the slide where it talks about hook bars?
What's up?
So that's saying the side cover is less than or equal to 2.5, right?
Wait.
For number 11 and smaller hooks.
If the side cover's more than 2.5 inches.
Greater?
Yeah.
Oh, I see.
Yep. Yeah, you want that's if you have ample amount of cover, then you're allowed to make a reduction.
We didn't have a Hallmark problem on hook.
No, but
Similar to.
it's just a different equation. So the other than the confinement, the factor and the cover, the factors are all the same. Like the epoxy factor, it's the same. Everything else that goes into the equation is the same. What? I'm trying to answer that as best I can. So, is it possible that you need to determine whether or not you have enough room for development? Yeah. But you'd have to know it was a hook if you needed to compute these. Because you need to know your dimensions. I mean, does that make sense? No, you don't know. You all seem done. I didn't say that. Yes. It's not wrong, but, I mean, it's not as efficient.
What's your tolerance going to be for the, like how close you have to get on the interaction mark?
Similar to all other interpolated values, I fully expect to be off a couple hundredths here and there. That's no big deal. If it's supposed to be 0.02 and you're looking at 9.86, you know, that's a problem. So. Wow, you all just seem really tired. What's that? I can't. I'm sorry. Well, not really, but you know. You want me to what?
I wish that was a joke.
All I can say is this. Take your equation, use the Laplace transform, pull everything over on the other side, use an inverse Laplace transform, bam.
So what is it? All I know is you put an L in front of it, but I don't know what else happens to it.
No, it's not an L. It's a fancy L.
In a real grading world, I would probably need 106% to pass.
This is what I can tell you about a Laplace transform. The idea of a Laplace transform is to take a function, let's say your equation's in terms of t, you transform it into an equation that's in terms of s. But the big idea is to remove the calculus from the equation. Instead of it being a differential equation, it becomes an algebraic equation. So when it becomes an algebraic equation, you can lump everything all over onto one side, then take an inverse Laplace transform to get it back to your original variable, and here's your answer. Do you know how long it has been since I have done a Laplace transform? A while.
Have you used it since college?
I used it in grad school.
Okay, so we do use it at some point later on in life.
Well, if you go to grad school.
Her notes, one, are doing the other one. Two, she told us that she feels like that we can connect with them better if she writes them out instead of typing them.
What does that mean?
She buries her examples in the middle of each random sentence. And the problem is we get notes Sunday at 8 p.m. and the next one is due Monday morning.
I can't do anything about that. I can't do anything about that.
So in grad school, how often do you use this?
Not very.
Okay. So I don't remember it.
So, what's the Greek letter that's our safety factor?
Alpha?
No, the other one.
Phi?
Okay. The squiggle. Phi.
That's circle stick.
Faux fum.
Dictionary.com says you're wrong. That's just what I like to say.
Was it GreekMistake.com?
It says 21st letter of the Greek alphabet has a little circle stick, and it says
You're right. There's stick circle and there's circle stick.
All I know is I totally get where you're coming from. I was in a fraternity that was Phi Kappa Gamma, but every scientific and engineering related class I was ever in said Phi. No, both. You know, I had professors from all over. They all said Phi. So. Seriously, I have no explanation as to why. I just.
Yeah, that's why I point that out. It could be like mistake. I mean, if
It's not a mistake.
counted that mistake, like, man, we're on like at least.
Hold on. Wait. Watch this. Tau is shear stress, right? But it's theta.
Hey, look, I don't disagree that we say it incorrectly.
What do you call it?
Theta tau. Yeah.
But we use tau for.
Never thought about that.
Theta tau.
Not as big of a deal as phi versus phi. That's a phi phi pho phi. Yeah, that's in everything.
I just said that.
I still just found it. We're done with this review. Where's Jake Davis?
He's doing some drums in Iowa.
No, he's fixing.
Also.
Hold on.
Also, my notes pronounce Will Schaefer, not Shaffer.
Yeah. No, hold on. I remember when my first class I ever taught here at Marshall was geomatics, and you were in that class. And I remember on day one, I asked everybody, I said, you know, if you have a name that you would like me to call you, let me know, tell me. And I even passed a sign-in sheet and said, you know, write your, you know, what you would like to be called. Week seven into the class, we're out doing leveling, and they kept saying, Blake, turn the thing around. I said, who the hell is Blake? He knows that. It's a joke with me and him for well, years now. So, but yeah. So, you could have told me.
Well, I was actually on Will, so I probably did write down Will, but I didn't like write the phonetics of my last name.
Hey, I get Mickelsons, so it's okay. Or the Mitchelsons. That's the. I've gotten that one before.
I like Dr. Nicholson and Dr. Dickinson.
What's that?
Dr. Nicholson and Dr. Dickinson.
Okay. All right. Let's talk about concrete design. I mean, goodness, I know that you all are down to the wire and just feeling like, man, I just don't care. But pressure, that's fluids. But we do have an exam on Monday, so I want to make sure that you all feel fine about it. So any questions at all? This is the time. This is the last time. So. Well, you can ask. I probably won't be able to answer.
Spiral tie spacing. This guy got different.
The what?
Spiral tie spacing.
On what? On just
Was problem 3.
problem 3?
Yeah, problem 2.
When I did the math, I ended up getting 2.51 inches. I just went with 2.5. So I had a column that was, I think it was 20 inches. So with cover, the core diameter is 17 inches, so the area of the core ended up being about 226 square inches. If I use a number 3 spiral, I say, all right, here's the diameter, here's the area. I can determine the minimum or the required reinforcement ratio and plug that into this to get the maximum spiral spacing. And I got a little over 2.5 inches, so I just went with 2.5. So that's fine. I will say this, with spirals, it's a lot of reinforcement. I mean, when we did ties, we would have tie spacing at like, what was it, 16 inches, 12 inches, you know. Spirals have been like 2 inches. So if you can get something simple like 2.5, I'd use it.
I thought that was
What?
forms.
It did? I was going to say, that doesn't make sense because I was lazy, so I didn't want to draw this image. That image comes from the solutions manual, so I was about to say. The column size, it would make sense if it came in 2 inches. So.
That's what the form size means. The outside diameter.
Yeah, yeah. It doesn't matter as long as you round to what I would call an even increment. I mean, I rounded up in this case, but the idea is that it doesn't matter because you're taking your actual gross area and plugging it into your steel, plugging it in to get your steel. If you were to take this and multiply by 0.02, that would be wrong. Does that make sense? Anything else? You do seem kind of cooked. I will say that. Just seem cooked. Yeah. What am I doing at about 4 o'clock? Oh, God.
4 to 6:30. And come on.
Did you have a question?
Yeah, so the spiral spacing.
Hold on.
Spiral spacing can be in whole inches and then go to the 2.5.
Yeah. Spiral spacing, I'd indicate that to the 1/2 inch. I mean, that's a lot of reinforcement. So if you can thin that up a little bit by using a 1/2 increment, do it.
Because I got that number to 2.5.
That's what we're going to look for on the solution.
I was watching your example following through, and I just assumed to like.
That's fine. That's no big deal. My eyes are itchy as well. I see everybody packing up. You all done?
Maximum hook length, like the hook length, going down, like set to like 12 inches or something like.
What?
The length of the hook, like going down, like
That is a standard. Yeah.
12 inches.
Well, hold on. I want to pull up both to kind of show you. It's 12 bar diameters. And this one, what I was getting at, because it was easier to show you, that dimension and that depth, that depends on the bar size. So, yep. That's just standardized. There's nothing really to invent there. No. Yeah, I didn't put that image there because, again, you don't have to design that. So. What's this?
Your grading scale isn't setting it up.
To what?
Doesn't go to 89.5.
I round up. I've told y'all that. I round up. If you get an 89.7 at the end of this semester, you get an A. I told you. I round up.
What is the 0.45?
That makes sense.
It's like that time we rounded, like 12 up to 15.
Yeah, I like that. Like an 85 becomes a 90.
Granted, that wasn't this class, that was Steve. But yeah.
It's the same professor.
That was for both.
Wait, what?
Yeah, what if our grade is a prom number?
That it's a prime number? I don't know.
When it was a prom number, what we're saying is in steel, like in the bolts, if it was a prom number, we just round it up to like 15 or something.
Those are bolt patterns, not grades. Now, I will admit, I did like what you all said in steel where you said, it's not curving the grade, it's cambering the grade. That's that was a good one. But,
When you put the load on it, flattens out.
but there is that, yeah, when I actually grade the test, it's sort of. Look, here's what I do. This is what I do. I put all the grades into an Excel spreadsheet. I compute your composite average. I round it to two numbers. And then I use that statement to determine whether or not it's an A, B, C, D, or F. That's what I do.
And 83 is a prom number for our time.
So I'll round it to 84.
Just say.
All right.
But
Oh.
you can't think of three numbers that are
One. An 83. Yes.
Explain to me this confinement factor stuff right here.
Okay.
What is it saying?
Hold on, let me. Okay. So the cover factor. So when you're determining development length, you're trying to determine how far this hook needs to be embedded into the adjacent shape. Now what the cover factor is saying is that if you have ample cover, over 2.5 inches on number 11 or smaller hooks, and 90-degree hooks if you've got 2 inches behind here. What that's saying is you've got ample cover and ample concrete to develop that rebar, so you can reduce that length, in this case, by 0.7. Does that make sense? Now, the confinement factor has to do with the stirrups, okay? In other words, that concrete that is around the hook is being confined by those stirrups, like being held together. That makes sense? All right. If you have a stirrup spacing that's less than or equal to 3 bar diameters, and this last increment is less than 2 bar diameters, then you can reduce it again by 0.8. And that's basically it. What? You looked at me and you had a smile. Oh, okay, okay.
So we multiply by 0.8. Why do they have both of those expressions?
7 and 0.8. Yes. Because if you go back one, your development length equation for hooks has the psi C and the psi R. So, that would be, you'd have 0.7 and 0.8 in here, so you would insert those. They'd just be other factors. So it's either 0.7 or 1 or 0.8 or 1. That's not too bad, right?
The cover factor, is it CB? Is that what that representing? Or am I mixing stuff together?
You're mixing stuff together.
Okay.
We're talking about, that's on the denominator on the straight bar factor.
Okay.
Sorry about that. Yeah, it's kind of the same symbol as in steel design. It's a little c, it's not a big C. It's understandable. But I do want to make sure that you all have exhausted every. I mean, if you don't have any questions, then you don't have any questions. But
I do applaud you for on review days not going over new material, because Dr. Wade thinks review days are just for, yeah, ask me 10 minutes of questions. Now let's move on to this new topic we're going to talk about today. I'm leaving early. You're the one that calls it.
yeah, well, my behavior, my pattern might be a little different if I had 75-minute classes. Like these are 50-minute classes, so. I think it would be tough to cover new material and have an exam review in 50 minutes. I just don't think it would work well. So. For not killing you? I haven't branched out into serial killing yet, so.
Yesterday, and my attendance in here is 100%, but in steel it's like a 95. And I suppose my question is, what's up with that?
We can look at it if you want. I have, let me let you know, I scan every single sign-in sheet. So if I miss one, I'll be the first person to admit it. So.
I'll come to you about that.
But I've had people who go to one and not go to the other.
Some people.
No, not talking about him. He said it. Yeah, I don't know. It might have been something back in January or something. I don't remember. But we can look at it here in a little bit if you want.
We did it.
Well, hold on. Switching it up, huh? Well, that's what I'm asking you all. Are we done?
Yes.
Yeah.
Okay, all right. Before we go, hold on. Are you good? You two good?
Yeah.
You good? You good, Mr. Fadiga? Is Link good? You two good? You three good over here? You four good in the back? You good, Mr. Lewis, Mr. Foreman, and you five? All right. So real quick, hold on. Give me a minute. Goodness. Look, if you all, most of you all were also in steel design, so unless I have you for a graduate course or for senior design, this is probably the last time I'll have you in class, so it's been an honor. For those of you that have not taken steel design, as far as I know, that's a class we'll offer every spring, so I'd love to have you in steel design. I think those of you that took steel design this semester, I would think you all seem to have fun, so hold on.
Are you going to be teaching secret design next spring?
I'm teaching it next fall, and that's, yeah, probably not, but I'm teaching it next fall. So,
Yeah.
well, wait till December and then hear from these 8 that are taking it from me next semester. Maybe they might give you a, what's that? Yeah.
Teaches the concept, like, for real, it does.
Not to you.
But I mean, like if you taught it, or if Hudson taught it, it wouldn't matter if it was a year or something, if you taught it later.
We kind of do it the same way. I mean, there is something to be said about that. It is what it is. Yeah.
The team beyond is the biggest thing. If you don't want to do it, said professor, don't be on that team.
Well, you all next semester, you're out of luck on that one. All I'll say is this: if this is the last time that I have you in class, it's been an absolute blast. My door and my inbox is always open. If you all have any questions or need anything, don't hesitate to contact me or ask me. I hope to have some of you in class again. If you haven't, if you haven't decided whether or not you want to take steel, I'd be happy to have you. With that being said, it's been a blast. When I first got here to Marshall, I was a steel guy, and then I found out, I'm teaching concrete design. I always had this joke that there's only two types of concrete, wet and cracked. But the more I got into teaching concrete design, the more fun I found that it was. This is actually a really fun class for me to teach. It goes outside my area a little bit, but I have a lot of fun doing it. I hope you've had fun as well. We will see you on Monday. One final reminder, if you haven't done your course evals, do them, and if I get 100% response, again, an additional 5 points goes your way. But I got to have 100%. That's the deal. All right. That's all I got. Ladies and gentlemen, we will see you on Monday. Oh, guys, stop with that. Stop with that. All right.